At 3:02 p.m. on a clear Friday afternoon in Chicago, American Airlines Flight 191 begins its takeoff roll from runway 32 at O'Hare International Airport. To the passengers seated inside the wide-body McDonnell Douglas DC-10, this is an ordinary departure to Los Angeles, another routine transcontinental flight in a long summer schedule. The cabin is calm. Seatbelts click. Engines roar with a familiar, reassuring power. Nothing in the atmosphere suggests that this aircraft is seconds away from becoming the deadliest aviation accident in United States history. The DC-10 accelerates past 100 knots. Inside the cockpit, Captain Walter Lux, First Officer James Dillard, and Flight Engineer Alfred Udovich monitor their instruments with practiced discipline. Their attention is focused forward, committed to the narrow corridor of runway and the precise timing required for rotation. The aircraft responds normally. Thrust is symmetrical. Airspeed builds steadily. There is no warning, no vibration, no hint of the catastrophic sequence already unfolding beneath the left wing. As the aircraft reaches rotation speed, Captain Lux gently pulls back on the control column. The nose lifts. The DC-10 leaves the ground, climbing into the afternoon sky. At that exact moment, a failure buried deep within the aircraft's maintenance history manifests itself with brutal finality. The number 1 engine, mounted on a pylon beneath the left wing, tears away from the aircraft. The massive turbofan pitches upward, ripping through hydraulic lines and electrical systems as it separates. In a fraction of a second, the engine slams into the wing, flips over the top, and disappears behind the aircraft, trailing debris across the runway below. Inside the cockpit, the crew does not see the engine depart. They feel no explosion. There is no dramatic bang, no shudder that clearly signals an engine separation. What they experience instead is confusion. Warning lights illuminate. Instruments behave erratically. Systems that should function independently begin to fail simultaneously. The left wing's leading-edge slats, powered by hydraulics severed in the separation, retract unexpectedly. On the flight deck, the cues are subtle, fragmented, and dangerously misleading. The DC-10 continues to climb, but asymmetrically. The loss of the engine itself is survivable. The aircraft is certified to fly with 1 engine out. What is not survivable is the silent aerodynamic betrayal now occurring on the left wing. With the slats retracted at low speed, the wing's lift capability is drastically reduced. The aircraft is flying on the edge of a stall, and the crew does not know it. As the jet climbs through 300 feet, the captain follows standard procedure for an engine failure after liftoff. He reduces pitch slightly and commands the retraction of flaps on schedule. To him, the aircraft feels heavy but manageable. There is no immediate indication that the left wing is approaching a critical angle of attack. The stall warning system, which relies on sensors powered by the very electrical lines torn away with the engine, remains silent. This silence is fatal. In the cockpit, the crew's attention is divided. They are dealing with a cascade of abnormal indications, none of which clearly point to the true nature of the emergency. The engine instruments show a failure, but not the kind that suggests total physical separation. Hydraulic pressure readings fluctuate. Electrical warnings appear inconsistent. Each pilot processes the situation through the lens of training and expectation, searching for a familiar pattern that does not exist. This is the first fracture in cockpit resource management. Information is incomplete, ambiguous, and fragmented. No single crew member has the full picture, and no one realizes how much information has been lost. The crew is responding to symptoms, not the underlying cause. The aircraft reaches approximately 450 feet above the ground. Airspeed begins to decay. The left wing, stripped of its high-lift devices, reaches its critical angle of attack before the right wing. Without warning, it stalls. The roll is sudden and violent. The DC-10 snaps left, banking sharply as lift on the left wing collapses. Captain Lux reacts instinctively, applying right aileron and rudder. But the controls are fighting physics. The right wing continues to generate lift while the left wing has effectively stopped flying. The aircraft rolls further left, passing 90 degrees of bank. Inside the cabin, passengers are thrown against their restraints as the floor becomes a wall. There is no time to understand what is happening. No announcement. No brace command. The aircraft is no longer climbing. It is falling, rotating, out of control. The cockpit voice recorder captures the crew's final seconds. Confusion gives way to alarm. Control inputs increase. The aircraft does not respond. One of the pilots exclaims in disbelief as the bank angle steepens. There is no discussion of a stall. There is no warning horn. The cues that should trigger an immediate nose-down recovery simply are not there. At approximately 325 feet above the ground, the DC-10 rolls fully inverted. Seconds later, it impacts an open field near a trailer park adjacent to the airport. The aircraft strikes the ground at high speed, cartwheeling in a fireball that sends black smoke towering into the Chicago sky. All 271 people on board are killed instantly. 2 people on the ground also lose their lives. Within minutes, emergency responders flood the scene. Fire crews battle intense flames fed by thousands of gallons of jet fuel. The wreckage is scattered across a wide debris field, the aircraft barely recognizable as an airliner. There are no survivors. The scale of destruction leaves no ambiguity about the severity of the event. As investigators from the National Transportation Safety Board arrive, one question dominates their thinking. How could a modern wide-body jet, flown by an experienced crew, crash seconds after takeoff on a clear day? The answer does not lie solely in the engine failure. It lies in the chain of decisions made months and years before the flight ever left the ground. The DC-10's #1 engine did not fail due to a design flaw alone. It failed because of how it was maintained. To save time and reduce labor costs, American Airlines had adopted an unofficial maintenance procedure that removed the engine and its pylon as a single unit, rather than separating them as specified by the manufacturer. This shortcut placed enormous stress on the pylon structure. Microscopic cracks formed. They went unnoticed. Over time, they grew. On Flight 191, those cracks reached their breaking point. When the engine tore away, it did far more than eliminate thrust. It destroyed redundant safety systems in a way no one had fully anticipated. Hydraulic lines for the slats were severed. Electrical power to critical warning systems was lost. The aircraft entered a configuration that mimicked a manageable engine failure while hiding a lethal aerodynamic condition. The crew was trained for engine failures. They were not trained for this. In the cockpit, there was no single error, no reckless decision, no obvious violation. What unfolded was a classic breakdown of situational awareness compounded by misleading information and the absence of effective cross-checking. The crew trusted their instruments because that trust is foundational to aviation safety. But on this flight, the instruments were lying by omission. The tragedy of Flight 191 is not just that an aircraft crashed. It is that everyone involved was doing what they believed was right, based on the information they had. The pilots followed procedures. Maintenance crews believed they were improving efficiency. Management believed cost savings did not compromise safety. Each decision, isolated and seemingly reasonable, aligned into a chain that could not be broken once the aircraft left the runway. In the days following the crash, the DC-10 fleet is grounded worldwide. Public confidence collapses. Investigators begin a painstaking reconstruction of the final seconds, the maintenance records, the engineering assumptions that allowed such a failure to remain hidden. What emerges is a sobering realization. Safety does not fail loudly. It fails quietly, incrementally, in places far removed from the cockpit, long before a pilot ever advances the throttles for takeoff. And on that afternoon in Chicago, those quiet failures finally demanded their price in the most unforgiving way possible. In the aftermath of the impact, the magnitude of the loss becomes immediately clear to investigators and first responders alike. The wreckage of the DC-10 is compact, violently fragmented, a signature of a high-energy crash with no attempt at recovery possible. This is not the debris field of an aircraft that struggled for control over miles. It is the footprint of a machine that was betrayed almost instantly after liftoff. For the National Transportation Safety Board, this distinction is critical. It narrows the timeline. It sharpens the focus. Whatever went wrong did so with terrifying speed. Early witness accounts describe a shocking sight. Several observers near the airport report seeing the left engine detach and flip over the wing just after takeoff. Others recall the aircraft climbing normally for a brief moment before rolling sharply left. These statements immediately steer investigators away from pilot sabotage or weather and toward a mechanical or structural failure. The flight data recorder, recovered quickly from the wreckage, confirms this sequence with cold precision. Engine parameters drop abruptly at rotation. Airspeed decays shortly afterward. Control inputs spike as the aircraft rolls beyond recoverable limits. The cockpit voice recorder reveals something more unsettling. There is no panic at first, only confusion. The crew acknowledges abnormal indications, but their conversation reflects a belief that the aircraft is still fundamentally controllable. There is no reference to a stall, no urgent call-out of asymmetric lift, no recognition that the left wing has entered an unrecoverable aerodynamic state. This absence becomes one of the most important clues in understanding how the accident unfolded. Investigators turn their attention to the DC-10's systems architecture. Unlike earlier aircraft, the DC-10 was designed with a high degree of redundancy, especially in hydraulics and flight controls. On paper, the loss of a single engine should not cripple the airplane. Yet the evidence shows that the engine separation did more than remove thrust. It acted like a surgical strike, severing multiple systems routed through the same physical space. When the engine tore away from the pylon, it ripped out hydraulic lines responsible for powering the leading-edge slats on the left wing. These slats are critical during takeoff and climb, allowing the wing to generate sufficient lift at low speeds. Without hydraulic pressure, the slats retracted automatically, even though the flaps remained extended. This created a configuration no pilot would ever intentionally command during climb. One wing was effectively in takeoff mode. The other was not. The design flaw was subtle but devastating. There was no cockpit indication that the slats had retracted. The crew had no direct feedback to tell them that the left wing's lift capability had been dramatically reduced. The aircraft's warning systems, designed to alert pilots to a stall, were electrically powered through circuits that had also been severed during the engine separation. The stall warning system was not merely delayed. It was dead. This meant the crew was flying blind in the most dangerous phase of flight. From a human factors perspective, this is where the accident becomes a case study in cognitive overload and false assumptions. The pilots were trained to respond to engine failures with a specific sequence of actions. Reduce pitch slightly, maintain climb speed, retract flaps on schedule. These procedures are drilled into muscle memory through countless simulator sessions. But procedures are only as good as the assumptions behind them. On Flight 191, the underlying assumptions were wrong. The crew believed they were dealing with a standard engine failure. In reality, they were facing a severe asymmetry in lift combined with degraded warning systems. Every action they took, while correct for an engine failure, pushed the aircraft closer to a stall on the left wing. When the captain retracted the flaps, he unknowingly reduced lift margin even further. When he maintained climb attitude, he unknowingly allowed airspeed to bleed away. This is not pilot error in the traditional sense. It is a failure of the system to communicate the truth to the humans responsible for controlling it. As the investigation deepens, attention shifts away from the cockpit and toward the maintenance hangars. Records reveal that American Airlines had modified the manufacturer's recommended engine removal procedure. Instead of detaching the engine from the pylon first, mechanics removed both as a single assembly using a forklift. The method saved hours of labor and reduced aircraft downtime. On paper, it seemed efficient. In practice, it introduced stress loads the pylon was never designed to endure. Microscopic cracks began forming at critical attachment points. These cracks were not visible during routine inspections. They grew slowly, silently, over multiple maintenance cycles. By the time Flight 191 taxied to the runway, the pylon structure was already compromised beyond recovery. The NTSB discovers that this maintenance shortcut was not isolated. Other airlines had experimented with similar procedures. Some had abandoned them after encountering minor damage. Others continued, unaware of the long-term consequences. The industry had drifted into a dangerous normalization of deviance, where deviations from approved procedures became accepted because no immediate failures occurred. Flight 191 was the moment when those deviations finally converged with catastrophic results. The concept of crew resource management, still in its infancy in 1979, looms large in the analysis. At the time, CRM was not the structured discipline it is today. Cockpit hierarchies were rigid. Communication tended to flow one way, from captain downward. In the confusion following the engine separation, there was little cross-checking of assumptions. No one challenged the mental model that this was a straightforward engine failure. No one questioned why multiple systems were failing simultaneously. The crew trusted the aircraft to tell them when something was critically wrong. It never did. This trust, deeply ingrained and usually justified, became a vulnerability. As investigators piece together the final seconds, a haunting pattern emerges. Had the crew known the slats were retracted, they could have maintained higher airspeed. Had the stall warning sounded, they might have instinctively lowered the nose. Had the engine separation been indicated clearly, procedures might have changed. But each layer of defense failed quietly, leaving the crew with just enough information to be confident and just enough ignorance to be doomed. The grounding of the DC-10 fleet sends shockwaves through the aviation world. Airlines scramble to reassure passengers. Engineers race to redesign systems. Regulators reevaluate certification standards that once seemed robust. The crash of Flight 191 becomes more than an accident. It becomes a referendum on how modern aviation balances efficiency, complexity, and human limits. In the wreckage outside O'Hare, investigators are not just looking at twisted metal. They are staring into a mirror that reflects the consequences of small compromises compounded over time. The field where the aircraft came to rest becomes a stark reminder that safety is not a static achievement. It is a continuous negotiation between humans, machines, and the systems that connect them. And in that negotiation, silence can be just as deadly as error. As the investigation progresses, the focus sharpens on how a technologically advanced aircraft could be rendered uncontrollable by a single mechanical event. The answer lies not in one failure, but in the way multiple safeguards were unknowingly routed through the same vulnerable space. The DC-10 was certified under assumptions that redundancy meant separation. In reality, critical systems converged physically near the engine pylon, creating a single point of catastrophic vulnerability. When the engine departed the wing, it did not simply fail. It took the aircraft's safety net with it. Engineers reconstruct the sequence in exhaustive detail. High-speed photography of the wreckage confirms that the pylon fractured upward and inward, consistent with overstress rather than fatigue alone. Metallurgical analysis reveals progressive cracking that had gone undetected for months. These cracks did not originate from flight loads. They originated from maintenance-induced stress, introduced repeatedly each time the engine and pylon were removed together. The procedure, never approved by the manufacturer, had quietly rewritten the aircraft's structural life expectancy. What makes this especially disturbing to investigators is how invisible the risk had been. Standard inspections were never designed to detect this type of damage. The cracks formed in areas not easily accessible without major disassembly. Maintenance crews followed checklists. Inspectors signed off on work orders. Each step appeared compliant. Yet the system was blind to the very hazard it had created. In the cockpit, the human consequences of that blindness were immediate. Simulator recreations conducted after the accident revealed that even experienced test pilots struggle to recognize the unfolding emergency. With no stall warning and no slat position indication, the aircraft behaves deceptively. Control forces feel heavy but not alarming. The roll onset occurs suddenly, with little tactile warning. Recovery margins are measured in seconds, and without advance awareness, they disappear almost instantly. This realization forces investigators to confront an uncomfortable truth. The crew of Flight 191 never truly had a chance. From a human factors standpoint, the accident exposes the limits of procedural thinking. Pilots are trained to categorize problems quickly. This is not a flaw. It is a survival mechanism in an environment where time is scarce and complexity is high. But categorization depends on cues. On Flight 191, the cues were incomplete and misleading. The aircraft presented the symptoms of an engine failure while concealing the far more dangerous reality of asymmetric lift loss. The crew's decision-making followed logic. That logic was built on false premises. The absence of assertive cross-checking in the cockpit reflects the era's culture. In 1979, crew resource management as a formal discipline was still emerging. Authority gradients were steep. Captains were expected to command. Subordinates were expected to support, not challenge. In high workload situations, questioning assumptions was not standard practice. The cockpit was efficient, but it was not resilient to ambiguity. Modern CRM training would later emphasize exactly what was missing that day, verbalizing uncertainty, sharing mental models, and actively searching for disconfirming evidence. But those concepts were not yet embedded in airline operations. The crew did not fail to communicate. They communicated within a framework that did not encourage deep challenge. As public scrutiny intensifies, American Airlines faces mounting pressure. The airline initially defends its maintenance practices, arguing that no regulations explicitly prohibited the engine pylon removal method. That defense begins to crumble as investigators demonstrate the direct link between the procedure and the failure. The issue is not regulatory loopholes. It is organizational mindset. Efficiency had been rewarded. Schedule reliability had been prioritized. Risk, subtle and delayed, had been discounted. The grounding of the DC-10 fleet becomes a defining moment. Airlines cancel hundreds of flights. Financial losses mount. Public confidence erodes. Yet within the disruption lies an opportunity. For the first time, regulators, manufacturers, and airlines confront the reality that safety cannot be compartmentalized. Maintenance decisions, design assumptions, and cockpit procedures are inseparable elements of a single system. The NTSB's findings are unequivocal. The probable cause is identified as the separation of the engine and pylon assembly due to improper maintenance procedures. Contributing factors include the vulnerability of the slat system to hydraulic failure, the loss of stall warning capability, and the lack of cockpit indications revealing the true aerodynamic state of the aircraft. Nowhere in the report is blame assigned to the pilots. Their actions are described as consistent with training and available information. This distinction matters. It reframes the narrative from individual failure to systemic breakdown. In the months that follow, sweeping changes are implemented. Maintenance procedures are rewritten and strictly enforced. Engine and pylon removal methods are standardized across the industry. Inspection protocols are expanded to detect stress-related damage previously considered unlikely. On the design side, manufacturers reassess system routing to ensure true redundancy, not just theoretical independence. Cockpit philosophy begins to shift as well. The accident becomes a foundational case study in the evolution of crew resource management. Training programs start emphasizing communication over hierarchy, inquiry over assumption. Pilots are taught not just to follow procedures, but to understand their limitations. The idea that an aircraft can fail in ways not covered by checklists becomes central to safety education. Flight 191 also reshapes how stall warnings and configuration alerts are designed. Redundancy is no longer enough if it shares common points of failure. Warning systems must survive multiple, cascading malfunctions. They must speak clearly, even when the aircraft is badly damaged. Silence, engineers now understand, is unacceptable. For the families of the victims, these changes come too late. Memorials rise near the crash site. Names are engraved in stone. The loss is permanent. Yet within aviation, the legacy of Flight 191 is profound. It becomes a turning point, a moment when complacency is exposed and complexity is taken seriously. The crash demonstrates that disasters are rarely sudden. They are usually the final act of a long, quiet story written far from the spotlight. In this case, that story began in maintenance hangars, in cost-benefit calculations, in assumptions about redundancy and human adaptability. By the time the aircraft reached the runway, the outcome was already sealed. As years pass, the DC-10 returns to service under stricter oversight. Its reputation recovers slowly, though never completely. The lessons learned from Flight 191 ripple outward, influencing aircraft certification, airline management, and pilot training across the world. The accident becomes more than a statistic. It becomes a warning etched into the collective memory of aviation. A warning that technology alone cannot guarantee safety, that procedures must be questioned, not just followed, and that when systems fail silently, even the most skilled hands can be rendered powerless. The story of Flight 191 is not just about how an aircraft fell from the sky. It is about how small deviations, accepted and repeated, can align into irreversible catastrophe. It is about the fragile boundary between routine and disaster, and how easily that boundary can be crossed without anyone noticing. In aviation, every accident rewrites the rules, and some, like this one, do so in letters large enough to be seen from every cockpit, hangar, and boardroom that dares to forget the cost of silence. In the years following the crash, the aviation industry undergoes a period of deep introspection. Flight 191 forces a collective reckoning with a reality that had been underestimated for decades. Accidents are rarely the result of a single dramatic failure. They are the outcome of systems that drift, quietly and incrementally, away from their original safety margins. The DC-10 did not betray its crew spontaneously. It reflected the sum of decisions made by engineers, managers, inspectors, and regulators who never expected their choices to intersect in a single moment of catastrophe. The investigation reveals that the concept of redundancy, long treated as a guarantee of safety, had been misunderstood. Redundancy on paper does not equal resilience in practice. The routing of hydraulic lines and electrical wiring through common physical spaces created hidden dependencies. When the engines separated, it acted as a single blow that collapsed multiple layers of defense simultaneously. This realization reshapes how aircraft systems are evaluated. Engineers begin to map not just functional redundancy, but physical and logical separation, asking not whether systems are duplicated, but whether they can fail together. Human factors specialists examine the crew's final moments with increasing nuance. The absence of overt panic on the cockpit voice recorder becomes a focal point. It suggests not complacency, but confidence. The crew believed they were managing a known problem. This confidence, normally a strength, became a liability because it delayed the recognition that the situation was fundamentally different from anything they had trained for. The accident underscores a paradox at the heart of aviation safety. Expertise can narrow perception under uncertainty. This insight drives a transformation in training philosophy. Pilots are no longer taught solely to execute procedures flawlessly. They are trained to question context, to recognize when a situation does not fit established patterns. The phrase aviate, navigate, communicate evolves from a mantra into a framework for managing ambiguity. Maintaining airspeed, understanding configuration, and preserving situational awareness become priorities even when procedures seem to demand otherwise. Flight simulators are updated to include scenarios that deliberately violate assumptions. Crews are exposed to failures that do not trigger expected warnings. They are challenged to identify what the aircraft is doing aerodynamically, not just what the instruments appear to say. This shift represents a cultural change. It acknowledges that human adaptability, not procedural rigidity, is the last line of defense when systems behave unexpectedly. Regulatory oversight also changes. The Federal Aviation Administration reevaluates how maintenance practices are approved and monitored. Informal deviations from manufacturer recommendations are no longer tolerated, even if they appear to save time without immediate consequence. The idea that efficiency can coexist harmlessly with safety shortcuts is dismantled. Documentation, traceability, and compliance become non-negotiable pillars of airline operations. The DC-10 itself becomes a test case for design philosophy. Modifications are mandated to ensure that critical warning systems remain functional even after severe damage. Slat position indicators are enhanced. Electrical routing is revised. Hydraulic system protections are reinforced. These changes are not cosmetic. They reflect a new understanding that pilots must never be deprived of essential information during high-risk phases of flight. Public perception of the aircraft, however, is slower to recover. The image of Flight 191 rolling inverted just seconds after takeoff is seared into collective memory. For many passengers, the DC-10 becomes synonymous with danger, regardless of statistical safety improvements. Airlines struggle to rebuild trust, emphasizing transparency and accountability in ways that were uncommon before the accident. Behind the scenes, safety analysts study the crash as a prototype of organizational failure. They identify warning signs that, in retrospect, were visible. Maintenance crews had reported difficulty aligning engines during reinstallation. Minor damage had been observed on pylons. These anomalies were treated as isolated issues rather than symptoms of a deeper problem. The organization lacked mechanisms to aggregate weak signals into actionable insight. This lesson extends beyond aviation. Flight 191 becomes a reference point in industries where complex systems and human operators intersect. Nuclear power, medicine, spaceflight, and maritime operations all draw from its findings. The principle is universal. When systems become complex, accidents emerge from interactions, not components. The human cost remains at the center of the narrative. Families of the victims push for accountability, not just compensation. Their advocacy contributes to reforms that prioritize safety over expedience. Memorials near O'Hare serve as reminders that behind every technical diagram and regulatory update are lives abruptly ended, futures erased without warning. For investigators, the most haunting aspect of Flight 191 is its inevitability. Once the engines separated, the outcome was sealed within seconds. No heroic maneuver, no last-second insight could have changed the physics at play. This realization reinforces a core tenet of accident prevention. The decisive moment often occurs long before the event itself. By the time humans are forced to react, the opportunity for recovery may already be gone. This understanding reshapes how accidents are framed. Blame is replaced with analysis. Questions shift from who failed to how the system allowed failure to propagate unchecked. Flight 191 accelerates this transition, helping to move aviation safety away from punitive models and toward learning-based approaches. The concept of crew resource management matures rapidly in the wake of the accident. Training programs emphasize flattening authority gradients, encouraging first officers and engineers to voice concerns without hesitation. The goal is not to undermine leadership, but to strengthen it through shared awareness. In this model, silence is recognized as a risk factor, not a virtue. Over time, these changes produce measurable results. Accident rates decline. Incident reporting increases. Pilots become more willing to discuss uncertainty and challenge assumptions. Maintenance organizations adopt stricter quality controls. Regulators demand evidence of safety culture, not just compliance. Yet the shadow of Flight 191 never fully recedes. It remains a benchmark against which new aircraft designs and operational practices are measured. Whenever cost pressures tempt organizations to deviate from established procedures, the crash is invoked as a cautionary tale. It stands as proof that the margin between efficiency and disaster can be dangerously thin. The accident also influences how aviation communicates risk to the public. Transparency becomes a strategic necessity. Airlines learn that trust is built not by denying problems, but by demonstrating a commitment to understanding and addressing them. This shift, though gradual, marks a fundamental change in the relationship between the industry and those it serves. As decades pass, the field near O'Hare transforms. What was once a scarred landscape of wreckage becomes quiet again. Planes continue to depart overhead, climbing smoothly into the sky. For most passengers, Flight 191 is a distant memory, a historical footnote. For those within the industry, it remains a living lesson. It reminds them that every checklist, every inspection, every training session carries weight. That safety is not an abstract concept, but a fragile construct sustained by vigilance at every level. And that when vigilance fades, even briefly, the consequences can be irreversible. Flight 191 did not change aviation because it was unique. It changed aviation because it revealed how ordinary decisions, made under ordinary pressures, can align into extraordinary tragedy. Its legacy endures not in fear, but in the discipline it instilled, and in the understanding that the true work of safety is never finished. The final lesson of American Airlines Flight 191 does not reside in a single broken component or a single flawed decision. It resides in the uncomfortable realization that modern aviation accidents are born long before an aircraft ever moves. By the time the DC-10 rolled inverted and fell out of the sky near O'Hare, the outcome was already locked in by a system that had slowly drifted away from its own safety assumptions. From a forensic standpoint, the NTSB's final report makes something unmistakably clear. The crash was not caused by pilot incompetence, nor by reckless behavior in the cockpit. The crew of Flight 191 responded in a manner consistent with their training and with the information available to them. The failure was systemic. It was embedded in maintenance practices, design vulnerabilities, certification philosophy, and organizational culture. The probable cause, as stated by the NTSB, was the separation of the number one engine and pylon assembly due to improper maintenance procedures. That statement, while technically accurate, only scratches the surface. The deeper cause was the acceptance of a shortcut that violated the manufacturer's intent and introduced structural damage that standard inspections were never designed to detect. Over time, that damage became normalized, invisible, and therefore inevitable. Equally critical were the contributing factors. The DC-10 system architecture allowed multiple critical systems to be routed through the same physical space. When the engine separated, it did not merely remove thrust. It destroyed hydraulic lines powering the leading-edge slats and severed electrical pathways feeding the stall warning system. The aircraft entered a lethal configuration without providing the crew any direct indication of what had changed. This was not a failure of redundancy. It was a failure of independence. Redundancy assumes that backup systems will remain available when primary systems fail. Flight 191 demonstrated that redundancy, without physical and functional separation, is an illusion. The aircraft technically had backups, but they were vulnerable to the same initiating event. One mechanical failure collapsed multiple layers of defense simultaneously. From a human factors perspective, the accident exposed how dangerous partial information can be. The crew was not overwhelmed by alarms. They were misled by silence. The absence of a stall warning reinforced the belief that the aircraft was still within safe aerodynamic margins. The lack of slat position indication prevented the crew from understanding why the aircraft's performance was degrading so rapidly. In aviation, incorrect feedback can be more dangerous than no feedback at all. The cockpit voice recorder underscores this tragedy. There is no chaos, no shouting, no recognition of impending loss of control. What it captures instead is a crew attempting to manage a familiar problem in an unfamiliar reality. This disconnect between perception and truth is at the heart of the accident. Crew resource management, as it exists today, was not yet fully developed in 1979. Authority gradients in cockpits were steep. Questioning assumptions was not standard behavior. The idea that an engine failure could mask a catastrophic aerodynamic condition was not part of operational thinking. In that environment, silence was interpreted as confirmation rather than warning. Flight 191 became one of the catalysts that forced this culture to change. In the years that followed, CRM evolved from a concept into a discipline. Training programs began emphasizing shared situational awareness, assertive communication, and the active challenging of assumptions. Pilots were taught that when multiple systems fail at once, the correct response may lie outside any checklist. The ability to step back, reassess, and question the aircraft's behavior became as important as procedural compliance. The accident also reshaped how maintenance operations were viewed. Informal deviations from approved procedures, even when well-intentioned, were no longer tolerated. The industry recognized that maintenance shortcuts rarely produce immediate consequences. Their danger lies in delayed failure, where cause and effect are separated by time, personnel, and context. After Flight 191, traceability and strict adherence to manufacturer guidance became central pillars of maintenance safety. Regulatory philosophy changed as well. Certification standards were reevaluated to account for common cause failures. Engineers began asking not whether systems were redundant, but whether they could be lost together. Warning systems were redesigned to survive severe damage and to communicate critical information even under degraded conditions. Silence, especially during high-risk phases of flight, was no longer acceptable. The DC-10 fleet eventually returned to service, modified and scrutinized. Statistically, it went on to operate safely for many years. Yet the shadow of Flight 191 never fully lifted. Public confidence recovered slowly, and only because the industry demonstrated tangible change. Transparency replaced denial. Investigation replaced defensiveness. Learning replaced blame. Beyond aviation, the crash influenced the broader field of safety science. Flight 191 became a textbook example of organizational accident theory. It illustrated how complex systems fail not because of a single broken part, but because of interactions between people, technology, and processes. It showed how warning signs can exist in isolation, yet fail to trigger action when organizations lack mechanisms to connect them. Maintenance crews had noticed alignment difficulties. Minor pylon damage had been observed. None of these signals, alone, appeared catastrophic. Together, they formed a clear warning that was never fully understood. The system did not lack information. It lacked integration. For the families of the victims, the investigation's conclusions brought clarity but not comfort. No procedural change can undo the loss of 273 lives. Yet their tragedy reshaped an industry that moves millions of people every day. Accidents that never happened, disasters that were quietly prevented, are part of Flight 191's invisible legacy. The field near O'Hare where the aircraft came to rest is unremarkable today. Aircraft continue to depart overhead, climbing smoothly into the sky. For most passengers, that flight is a distant historical footnote. For those who work in aviation, it remains a constant reference point. A reminder that the most dangerous failures are often the ones no one expects, the ones hidden behind routine success. Flight 191 also reinforces a fundamental truth about aviation safety. The decisive moment of an accident rarely occurs in the cockpit. It occurs in design offices, maintenance hangars, management meetings, and regulatory frameworks. By the time pilots are forced to react, the window for recovery may already be closed. This understanding reshapes responsibility. Safety is not the burden of the last person in the chain. It is a collective obligation distributed across every decision that shapes how an aircraft is built, maintained, and operated. When any part of that system drifts, the consequences can be swift and unforgiving. In the end, American Airlines Flight 191 stands as one of the clearest demonstrations that modern aviation accidents are not mysteries. They are stories. Stories written slowly, quietly, and often invisibly, until a single moment reveals everything at once. Every flight has a history, even before it leaves the ground. Some histories end uneventfully, forgotten as soon as the wheels touch down. Others, like Flight 191, are written into the foundation of aviation itself. In that lesson, paid for at an immeasurable cost, remains etched in the skies above Chicago, reminding the industry that safety is not defined by what works most of the time, but by what prevents catastrophe when everything goes wrong.